Okay, I realize I am not done. I still have a hence part question that asks you to find the value of tangent 15 degrees times tangent of 75 degrees. Now, notice that actually this is just a slight uh, change from the previous part 2 question. All that you need to realize is that the trick you need to realize is that tangent of A, okay, don't say A, let's say theta. Theta is really just sine of theta over cosine of theta. And can you see how these two are related? Sine 15 degrees, sine 75 degrees, tangent 15 degrees, tangent 75 degrees. They both have 15 and 75 degrees. So what this means is that when we want to find out tangent 15 degrees times tangent of 75 degrees, it's really just sine 15 degrees times sine of 75 degrees, all divided by cosine of 15 degrees times cosine of 15 degrees. Oh, okay, that's cool. We simply have tangent substituted with sine over cosine, tangent substituted with sine over cosine. Fine, fair enough. But notice that the numerator sine 15 times sine 75, we already found out that it is 14 degrees. But what about the cosine 15 degrees and... Sorry, this should be a 75. My bad. How about this cosine 15 degrees and cosine 75 degrees? That's when you have to know complementary identities. You see, complementary identities, cosine of a alpha is equal to a sine of a beta. This trick, when the alpha plus beta adds up to 90 degrees. Don't care what the alpha and beta is, as long as those two angles inside add up to 90 degrees, then you can have cosine equals to sine. The co of the sine is equal to the sine. Co of the sine is equal to the of the sine. Okay? Co of the sine is equal to sine. Nothing sine. This is called complementary identities. There are similar identities for cosecant and just secant, cotangent and just tangent. It's really the same rule. I'll just explain it now. If you say the angle is alpha and then the angle is beta here, angle is alpha, the angle here is a beta, it all follows the same rule. Cosecant equals to secant, cotangent equals to tangent, as long as alpha plus beta adds up to 90 degrees. But for this case, you don't need these identities, you only need this one. You only need... Okay, in fact, this is actually a bit inaccurate when I say cosine equals to sine. I never include the angle here, which makes things inaccurate. So, yeah, I think I'll just erase this. This is confusing. I'll erase this part. Just need to know this part. Just need to know this part. Now, take note that cosine of 15 degrees. What's the complement of 15 degrees? In other words, what's something plus 15 degrees adds up to 90 degrees? It's really just 90 minus 15, right? If you type in your calculator, you should get 75 degrees. So what this means is that cosine 15 degrees is really just sine 75 degrees. Correct? Sine 75 degrees. But what about cosine of 75 degrees? What's the complement of 75 degrees? Oh, you realize it's really just 15 degrees. So this is the same as sine of 15 degrees. That looks very familiar. This expression. Isn't that what I saw at the top? So let's say at this very start, right, at this very beginning, I didn't replace my 1 over 4. I just copy and paste the top. Copy and paste. But then I realized, the denominator, because of complementary identities, I managed to convert it into this form, because of complementary identities. So what does this mean? It means that you look at the top and the bottom. What you realize is that they both share the same common factor. Sine 75 degrees, cancel off. Sine 15 degrees, cancel off. What are you left with? 0? Is it 0? No. When you cancel off, you're left with a factor of 1. Okay? When you sort of cancel off the top and the bottom, you're left with in its place, the sine of 75 degrees. When it got cancelled off, it's replaced with a 1 that's being multiplied onto whatever is remaining. Okay, you can think of it that way. So what you're left with at the end of the day is 1 times 1 divided by 1 times 1, which is nothing but 1. And then we are done.